Yes, thank you so much, Dr. Suda, for this very interesting presentation about the possibility to use ammonia as fuel for industrial purpose or more globally for energy sector. The last talk will be done by Dr. Albert Lanser. He's working for Duiker Combustion Engineering for over 30 years and has held multiple positions in project execution. The current role within Duiker is Business Development Director. He has a background in mechanical engineering and is active in the field of ammonia as a carbon-free fuel for industry. He has been actively involved in Duiker's latest research of the combustion of ammonia in combination with hydrogen sulphide and water, based on Duiker stoichiometry control oxidation technology. Please, Albert.
Okay, thank you, Christine. I will try to share my presentation. Yes. Okay.
Yes, it's okay.
It's okay? Okay. Well, good morning, everybody. Thank you for attending my presentation. I'm just trying to open button, the laser pointer. Yes, okay. Yeah, I find it inspiring to tell you more about Duiker's experience in commercial applications for ammonia combustion. The next slide is an overview of the contents that my presentation will address. First of all, I will give you a short introduction of our company. Also, what is important is that there are some reasons why Duiker developed an ammonia combustion technology, and I will give you some of the background in that. Then I'll go to the introduction to our stoichiometric controlled oxidation. In short, it's SCO technology. Furthermore, I will give you some examples of industrial scale ammonia combustion systems based on our SCO technology, which are already in operation. Based on the SCO units in operation, we can share some of our experiences in combustion of ammonia. And the last thing that I would like to address is to give you some oversight of new industrial applications for ammonia combustion. I'm going to the next slide to give you some idea of Duiker as a company. Yeah, our core business is development, engineering, supply, and servicing of combustion and process equipment. A typical example of a combustion system is in the right corner of the slide. This is what we call the LMV high intensity burner. And let's go till the flanged connection. And from this flanged connection till the tube sheet, you see the part that we recognize as the main reaction furnace. And after the tube sheet, the heat generated from the combustion will be transferred to the water that is surrounding these pipes and will form steam, and that will be collected in a steam drum. And the next slide will tell you more about our focuses. Our first pillar of our focus is Selfrecovery solutions. On the picture, you see here one single burner, which is a very large burner. You can see the people standing in front of the burner. The outside diameter of this typical burner for Selfrecovery solutions is 4.8 meters. And the combustion air amount that is used per hour is 120 tons. So it's a very large capacity burner, which is used for self-recovery. And I will give you some background later on the self-recovery units. In the bottom, there's also a picture of another type, LMV burner, just to show you that there are different types. And this special type normally is being applied in revamp situations. The second focus is on the conversion of sustainable fuels. Amongst others, the most famous are, of course, ammonia and hydrogen. This is already a sneak preview of our SEO unit that we have been designing and developed for the first customer. And in the bottom, you see an output, temperature output, based on the computational fluid dynamics that we have in-house, and this is particular for the development of hydrogen combustion. Last but not least, we also have a focus on emission reduction and energy savings. And in principle, this is the most cheapest and easiest way to decarbonize the industry. The next slide will give you some impression of our locations. Well, this is our main office. It's located in the Netherlands. In the main office in the Netherlands, we do basically the majority of the work in terms of developing, designing, and project management, and also starting field services. Our China office is a support office for sales and project management, as well as first-line services. We also have our own testing facilities, and that is located behind our office in this building. And when you walk around this building and you look from the other side, you will see the chimney on the roof of this part of the building. In the front, you see a small test LMV burner bolted on our blue-colored vessel, which is in fact a double-walled water-fill furnace in which we can do all kinds of tests. And the order of magnitude that we can generate heat is about 3 to 3.5 megawatts based on natural gas firing. So that was in fact a short introduction of our company. And the next slide, I will tell you something about the background for developing an ammonia combustion technology. And I do that, we tell you something about, well, starting with fossil fuels. Crude oil contains sulfur and nitrogen, and you do not want to have the sulfur or nitrogen in your final end products. So before you are making diesel or gasoline, a refinery is going to remove these pieces by a so-called process hydrodesulfurization. At the end of the hydrodesulfurization process, you get as a result H2S and ammonia. And in most cases in the refinery, these gases are both further processed in a Selfrecovery unit, which is operating on the so-called KAUST process. And in fact, a Selfrecovery unit reduced the SO2 emissions of an oil refinery to a large extent to prevent the forming of acid rain, which was one of the biggest environmental problems during the 70s and early of the previous century. If you do not combust the ammonia in the feed gas on a proper way, you may get problems in the way that the ammonia is forming some sulfur ammonium salts, and these are able to plug further downstream corrosion and further downstream equipment. And the picture, what you can see here, is just a tube sheet that has been plugged in a large extent. You can imagine that this is a problem for the operation of the Selfrecovery unit when the ammonia is not properly combusted. Moreover, if you have to remove these deposits, it is hardly impossible, which means that the complete SRU has to be taken out of operation. And in this particular example for tube sheet, you have to renew the tube sheet in its entirety to remove the plugging problem. So you can imagine that once the feed for a self-recovery unit contains considerable amounts of ammonia, the asset owner of refinery is worried about this fact. And for that reason, Duiker has developed a principle to combust ammonia in such a way that we want to combust all the ammonia, whilst we would like to maintain a very low NOx emission profile. One remark at the front, the SCO technology is proprietary knowledge, and so I cannot reveal too much details, but I will do my best to give you the relevant information so you can understand the principle. When we look to the SCO principle, it is basically consisting of two different combustion zones. The first stage is oxygen deficient, so there's a lack of oxygen in the first stage. After this stage, the flue gases just go to the second stage, where there's an excess oxygen situation. Before the second combustion step takes place, we add some quench medium in order to reduce the temperature here. The temperature in the first stage depends, of course, of the composition of the ammonia gas. It's not always 100% ammonia. We see often cases where there is some dilution with water, or with CO2, or with hydrocarbons, and even traces of H2S gas. So the temperature here varies between, let's say, 1300 to 1600 degrees. And the temperature that we want to maintain here is somewhere between 800 to 850 degrees C. The performance of the entire SCO unit depends on several things. First of all, we have a very high intensity mixing burner that generates high temperatures and an excellent mixing. And also the residence time that the gases are present inside the reactors is a part of our control philosophy. And the control philosophy and the type of burner is very fixed item of the SCO principle. This is the principle and theory. In the meantime, we have done tests with 100% ammonia, but also mixes with 50% water, 50% ammonia. Just for the record, the ammonia that I'm talking about is always in the gaseous form, so not on the liquid form. We already saw some picture of the first SCO unit that we have developed. I talked just about the first stage. Well, in fact, this is what the first stage is about. This is the LNV mixing burner, and the ammonia inlet is on the top, and the combusting air inlet is here installed. So after this combusting part, the flue gases will be transported to the second stage, which is the lower part of the vessel. And just for the record, there are two of these kinds of piping elbows. The one is on the other side, is hardly visible, but just for the record, there are two of these elbows with transporting the flue gas from the first stage to the second stage. In the second stage, we also add combustion air. And in this case, we have used tail gas from the Selfrecovery unit as a quench medium, which needed also be to oxidized in the second stage. So we made a very combination of firing ammonia, using the heat from this ammonia to oxidize the tail gas from the Selfrecovery unit. I will show you in the next slide some more of these details, but this is how the equipment looks like that forms the first SEO unit that we have been developed. The next slide is just a simplified picture of a Selfrecovery unit. This is the thermal stage, which is also some combustor in its scope. This is the catalytic state. The formed liquid sulfur will be collected here and will be stored to a liquid sulfur storage, where it will also further be degassed. After the catalytic section, the tail gas still contains some H2S, which is not allowed to be emitted through the stack. So there is also some tail gas treating unit, which produce some tail gas that only contains very minor parts of H2S, which then will be oxidized in an incinerator and then go to the stack. Well, this is without the SEO, and the configuration for the Selfrecovery unit with the SEO is a slightly different picture, but here you can see the Selfrecovery unit. Here we have the tail gas treating unit, which is in fact this same function as that. And here we have the tail gas. And in fact, here we have the SEO unit in the integration with the Selfrecovery unit. We have the ammonia, which is coming from a sour water stripper, two-stage a stripper that strips the H2S from the ammonia. The H2S goes directly to the Selfrecovery unit, and the ammonia is being used as a feedstock or a fuel for the first stage of the SEO unit. The flue gases with the high temperature will go to the second stage. There, the tail gas will come in and will quench the flue gas till the desired oxidation temperature, so that the emissions comply with the permits of the refinery and then go to the stack. Just for the record, there is no further flue gas cleanup necessary in order to comply with the permits for the refinery. So that gives already a signal that the NOx performed, or the NOx generation in the SEO, is quite low. How does the equipment look like? Well, this is the one that we already saw in the previous slides. The first stage is on top. The second stage is the lower vessel. The reason why these two stages were on top of each other was just a customer requirement. The plot space was too little to have both units in line. Another application on the left spot is where the first stage and the second stage are installed in line. And this is the SEO burner. This is the first stage till the orifice in the refractory lining, and this is the second stage. So depending on the composition of the feeds, the requirements of the emissions, we calculate the residence times and the temperatures that are necessary in both sections, and we calculate the stoichiometry. These two units have been installed in refineries. Here you can recognize the elbow piping from the first to the second stage. This installation has been installed in a refinery in Western Europe. Well, the refinery is in operation because you can see some steam clouds here on top of the SEO unit, and the maximum ammonia flow that we have designed for was 800 kilograms per hour. The other one, which is in fact the inline vessel that I have shown you on the previous slide, is installed in a refinery in China, and this was slightly bigger. This one has a maximum ammonia flow of 2,684 kilograms per hour. In the meantime, we have supplied 5 industrial commercial SEO applications for the industry, and 3 of them are already in operation. And during operation, we were sometimes in a position to do some comprehensive measurements, which I will use for the next slide. Because most of the important things that we measured is that the NOx formation in our SEO units measured after the second stage is about 50 to 80 parts per million in volume based upon 3% oxygen in the dry flue gases, so without the water content. It also appeared that the SEO combustion process is a very robust process because it's capable to oxidize ammonia in a variety of compositions in the feed with other chemicals such as water, CO2, hydrocarbons, or even H2S. The ammonia flow ranges that we have applied so far is for our ammonia test unit was quite very small. It's only 1.5 kilograms per hour. And the largest SEO unit we supplied today is the one you saw on the previous picture is 2,684 kilograms per hour, which give, if you express it in a thermal input range based on the lower heating value of ammonia of 80.6 megawatts per kilogram, you get for the ammonia test unit 7.9 kilowatts, and for the largest SEO unit till today, 30.9 megawatts. Yeah, you have seen the very big LMV burner in one of the first slides. And that means that the SEO combustion process is very good scalable. And we even can go to 200 megawatts for a single unit. So to give you some example to what extent this technology is scalable to. Yeah, the flame color is a very tricky one because I added some picture of our test furnace, and you see some light eliminating from the side glass. But when you look to the side glass, due to the LMV type burner, the mixing is very intense. You will not recognize the flame. What you see is that there's a refractory lining inside the reactor that's becoming hot, and it just radiating some light. So if there would any color, we should say, well, something like yellowish and some yellow color, but it's not really a flame that you can distinguish when you look to the side glass. Yeah, we have also done a new research for an SEO application. So we have done some tests, and we have done tests with ammonia-rich gas, where the H2S content was quite high. We did that in consultation with one of the larger oil companies. And the purpose of the test was to demonstrate the performance of the SEO technology based on gas flow, which were in fact sour water gas streams. And that is a typical feed stream to self-recovery units containing water, H2S, and ammonia. And in the next slide, you see the test installation. This is a picture of our ammonia test installation. And you can see also some further picture, it's further away, you can see the stack which is going to the roof. This is the general overview, schematic overview of the SEO test unit. We have a high intensity SEO burner, but also an SEO reactor furnace. And the stoichiometry is actively controlled both in the first as well as in the second stage. And it's not a fixed value, it's a dynamic value. In this case, the quench medium was steam. and we used also air for the oxidizing part in this test configuration. The SCO flue gas in this case also contained SO2. So the SO2 needs to go to a capture installation because that was not allowed to emit directly into the environment. We have done test runs with 20 to 50% of ammonia and 50 to 80% of H2S. And the NOx emissions that we have measured during these tests were in a range of 55 to 60 parts per million, based on 2% oxygen in the wet flue gases. There was some very small content of water. So this was the test that we have done to show the robustness of the SCO technology when there were large contaminations of H2S in the gas. Next slide, I will show you some new developments. One of the SCO applications that we are looking right now is a green ammonia fired steam generator. This is just a schematic overview, but it gives you some idea how we can use or make use of heat exchangers integrated in the SCO system to, for instance, warm up boiler feed water and transfer it into steam. And even that steam could be converted to superheated steam in a much higher temperature field in the first stage of the SCO combustion. So here you can use the green ammonia just as a fuel to turn water into steam. And just an example, and to show you another example, is the so-called ammonia cracker. An ammonia cracker is used to crack the ammonia through an ammonia cracking system into pure hydrogen. And here we use the ammonia as the energy for the cracking process itself. The ammonia throughput that the Duiker ammonia cracker can handle starts from 2 tons per hour till world scale needs, because it's scalable to very large quantities. The key technology that we use in our ammonia cracking process is our SCO technology. And it's a large functionality because it's an integrated solution from liquid ammonia to high purity hydrogen that comes out of the process. To give some more details about this black box, I show you the next slide, which is of course also some proprietary information, so it's not very detailed, but once you get the ammonia here, it's considered like a black box process. We have an integrated SCO technology inside our ammonia cracking process. The heating and cracking is optimized, and also the heat recovery. The ammonia generates heat, and it is very efficiently used inside this cracking process. And at the end, the purification of the hydrogen is also integrated in our ammonia cracking process. And it's even possible to supply pure hydrogen for fuel cell quality. I'm coming to the end of my presentation. Our motto is thousands of process solutions. You can rely on our experience. And that's because we already have supplied more than 2,000 combustion process solutions worldwide. I'd like to thank you for your attention to my presentation. And I understand from Christine that the questions will be handled in the panel session afterwards. Okay.
Exactly. Thank you so much, Albert, for the very interesting new approach about ammonia as fuel.